Me, myself, Johnu George. I'm technical director at Nutanix, primarily leading AI efforts, leading a couple of open source efforts as well in Kubeflow and the ML common storage. With me, Shiv Jha. He's a staff at Nutanix, leading the data platforms. He's a core contributor to many data and streaming platforms, including MySQL, Pulsar, and ClickHouse. So we'll briefly cover Kubeflow, the ML training architecture, and the challenges involved with that, and possible solutions, and what we have come up with, particularly a new data stack, which is addressing many of the solutions problems that we have talked about, and with sampled code. So we'll start with a basic MLOps pipeline for people who are new to this. So here we are talking about two different personas, right? One is a data scientist persona who's looking at the higher level language, knows just about Python, doesn't know anything about infrastructure. While there's a platform admin who looks at the cluster resources and ensure that the cluster is performant enough to handle all the operations. So here, for example, a data scientist comes in, he has some data. So he does some data preparation. Post that, he develops a basic model, POC model in Jupyter Notebook. Once he sees that his POC is good enough, he wants to scale it up using some kind of trainer. That is your full model development part, right? Where it will be a distributed training, scaling across multiple nodes using hundreds of GPUs. He gets a full-blown ML model out of that. Coupled with it, you do some tuning techniques, kind of like hyperparameter optimization. There are many techniques there where you optimize your model. And over time, you would have created many versions of models. And that is where model registry comes in, where you track all the versions of model, puts that in model registry. And once you have version models, you use your model serving to deploy a model specific to a version. And over time, you'll have newer versions, and then you do all kinds of deployment rollout strategies, where canary, blue-green deployment, etc., which is supported in the model serving component. And altogether, you have an ML pipeline which can orchestrate this entire workflow based on your requirements. So from a Kubeflow perspective, you get components which can tackle each and every phase of your MLOps cycle. In case of data preparation, there is a Spark operator which can through which you can submit Spark jobs. You have Kubeflow notebooks for notebook service, Kubeflow trainer for large-scale distributed training, Kubeflow Catib for hyperparameter optimization and other model tuning techniques, Kesa for model serving. For model registry requirements, there is model registry, Kubeflow model registry. And as a workflow engine, we have Kubeflow pipelines. So in this talk, we'll primarily look at the trainer part, which is the distributed training component. We have two personas as we discussed. The AI practitioner primarily looks at Python SDK, where he is comfortable with writing high-level Python data science code, which gets translated to a train job, which is the CRD, part of the trainer. The platform admins interact with the cluster using standard kubectl, and once it is submitted, the training job controller picks it up, and it is translated internally. It is using JobSet, which is a Kubernetes 6 project, which can create multiple jobs, which can orchestrate multiple jobs, Kubernetes batch jobs. So before getting to challenges, I just want to highlight what an ML training process looks like. So you have some data set with you in configured storage. You would have kept it after doing all data cleaning. Then during the training process, you load data in parallel to some kind of prefetch buffer, which is in CPU memory. Then you do some minimal transformation. You don't want to do extensive transformation during a training cycle for many reasons that we will talk about. So you do minimal transformation on the fly. And the final transform data is loaded in batches to various accelerator where the actual training happens. So in case of multi-node ML training, I'm just talking about the distributed data parallel, which is DDP. There are other techniques as well. Everything remains same. If you see that, in each node, it does the same, except that the data that is fed into each node is sharded. So you have a bigger data set. The idea is you shard data set into multiple splits, which is sent to multiple nodes. So from a PyTorch perspective, PyTorch is the one which is taking care of splitting it. But your storage should have the ability to provide shards which can be loaded to different nodes. So here, what are the challenges that we are talking about in an ML stack? So in general, for deep learning, more data means better model. So you need efficient storage for large data sets. We are talking about terabytes of data. In case of LLMs, we are, say, trillions of tokens are trained. And a bigger problem is the GPU underutilization. So if you see on the right side, it's a sample training code, which is a core training loop that we have in any ML training of a deep learning network. So there are two for loops. One is your number of epochs. One epoch is one dataset iteration. So you would do with n number of epochs, which actually means there are n dataset iterations where your user can configure that. In one epoch, you go through the entire dataset in batches. That is the second part, the training loader. So it is a customizable function in PyTorch where you say, I need batches of data for my training function. So in my training function, you take data, you do a forward pass, which is basically getting from your first layer to the last layer. You get some value, which might be deviated from an expected value. You calculate loss. And using the loss function, you do a backward pass where your final loss values are merged back to, in a way, your weights are updated to reflect your loss function. And it continues for full batch where one iteration gets over, which is one epoch, and then you continue for n epochs. So the key point here is when GPU is doing the training loop, on the top you would see a training loader, right, which is basically an async storage access. So while your GPU is computing, you need to provide data ready for the next GPU compute. So if you look at a graph, you should see continuous GPU compute cycles so that you don't want kind of like a interval where GPU is free, right? Which is essentially saying I'm underutilizing GPU. So storage has to provide enough throughput in order to make GPU busy throughout your training cycle. So that is a requirement from a storage perspective. So GPU underutilization happens when the storage can't keep up with the GPU compute. So in MLPerf and the storage which I am leading, we have got numbers which is way higher for many of the workloads. We are talking about gigabytes of data per second in order to satisfy a H100 or a higher end GPU. That is a requirement from a storage side. The other part is sharding of data across workers, where each worker needs some unique subset of data. And we have seen in the previous one where each shard is the one which we are giving to each of the node. So the storage has to support sharding of data, which has to be done efficiently and sent to each of the node. The other point is about shuffling. So in case of any deep learning network, the data is shuffled between epochs for multiple reasons to ensure that you are not overfitting to data. There are many reasons to that. So shuffling means you have to provide different data distribution in each epoch. So you don't say you have an order in first epoch, your order has to be different in the second epoch. So this is particularly challenging in case of storage because you are basically saying that I have read some data in the first epoch, I need a new kind of data in the second one. So if you do it in a raw manner, you have to restream data in every epoch, which is a wastage of network I/O. And the one common use case in enterprise setup would be supporting heterogeneous training jobs. So you have one data set, but multiple teams can start training jobs in parallel using the same data set. Now, one training job can actually use 5 workers, the other one can have 10 workers, right? So the question is, if you have a static data sharding pattern, how can you provide a shard of data across two jobs which have different kinds of workers? So these are the higher level challenges. I'll give to Shiv for the next slide.
Yeah. Thanks, Johnu, for setting up the stage for discussing next-gen data stack that we will discuss to tackle the challenges we just discussed in the last slide. So one of the first challenges that you would think with ML training is that you need lots of data, right? And if you have a huge amount of data, you care about storage cost. What do? Use something like an Apache Parquet. So we propose that you'll use a cloud-based product like S3 or a similar product, and then have a bucket where you put in all your Parquet files. Parquet, by the way, has amazing compression numbers. For instance, if you took a huge batch of CSV file and compared it against Parquet file, you would at least without any tuning have around 5x less storage, right? And if you tune it well and design the schema around Parquet, you could probably get better numbers. So lower storage, and when you are fetching data, lower amount of bytes across the wire, right? So storage cost and network cost both alleviated there. Now, when you have a lot of data files, you want an easy way to access it, right? No prices for guessing. SQL is something that's everywhere. So why not have an SQL layer on top of that data and use Apache Iceberg, let's say, for it. Lakehouse based off S3, which provides you infinite storage and really good HA characteristics. It's around 11 nines, if my memory serves right? Apache Iceberg is basically a spec. It's not a solution or a database service where you get a URL. And for this spec, there are a lot of vendors who provide solutions into it, right? So if you have Apache Iceberg solution, you can have your operational databases like a Postgres or MySQL or something like that landing into Apache Iceberg. A streaming data could also land up into Apache Iceberg. And you also have analytics databases and stream processing and whatnot, everything landing into Apache Iceberg based solutions. The other part of Iceberg is because you have a lot of integrations, you can have the same batch of data and you can access it in different ways depending on the requirements of your app, whatever access pattern it may be. But it's not a better process. You are fetching data on S3, right? So it's slower, right? You want data to be closer and customized for your access. The other problem could be that transferring data from S3 all the time is costly, especially if you have a lot of data. It multiplies. So what do? Let's take an analogy, right? Last talk, last section. Let's take an analogy because it's a little bit deeper internals on data architecture. Let's take the subway analogy, right? If you think of it, right, you have a warehouse where you have a bulk storage, all the frozen veggies and stuff, meat, sausages, whatnot. And on the other end, we have our chefs, right, who are preparing your orders and delivering it to you. You don't want all these guys to always go to the warehouse, pick up veggies, warm, chop, and everything, right? In a subway, when you go to it, they have the veggies, sort of the lady in the middle in this picture goes, pulls what's needed, warms it, chops it, cleans it, keeps it ready for the chef to just sort of put it out there for whatever you want and serve it to you. So the throughput is higher on the access there, right? So our takeaway from here is keep the data ready in a way that these guys can consume very easily. And when we talk of it, getting back to the technology piece, right? We are talking about the PyTorch training workers, right? One of the challenges that Johnu mentioned previously was we want to keep these workers busy. GPU is costly. You want to use every inch of it. So keep it in the cache and keep it in a way that is easily available, not wasting GPU time waiting for the data or The other part that we want to highlight is the cache is completely built on CPUs, right? So while the GPUs are doing an epoch of training, and they are now available to do next batch of training, then you have data in the cache prepared by CPUs to be made available for GPUs to directly access and access very quickly over the wire. Let's deep dive a bit into how will you load this cache, right? The arrow shows you that you have Parquet data sitting on S3, which has to land into my cache. My cache is built on a technology called Apache Arrow as the storage format. Now, what's the difference? Parquet is a storage format, columnar storage format in that, and it is optimized for making sure that the data on disk, right? Behind S3, there is a disk somewhere in the world, right? And it will store it very efficiently for disk. You also want data when it is in memory, cached there, to be available very, very quickly to your training workers. So Apache Arrow does that for us. We keep the cache data in an arrow format, and it's great for storage and transport, like we will see going ahead. But cache is a bunch of nodes, a cluster that for us, in simple terms, converts Parquet data to arrow record batches. Let's dive a little bit more inside the cache layer, right? How is the loading really happening? So the cache architecture in this snippet you see on the right has a head node and a bunch of data nodes. Sort of to keep the picture clear, we only have 2 data nodes. In a practical setting, you would probably have more. Again, stressed example where data sets, let's say, are very low for illustration. Let's say you have 100 files in Iceberg table, and you want to sort of go to the head node, try to query the meta data information of the Iceberg table, which basically tells you that, you know what, I have 100 odd files, and the head node makes assignments. So if we have 2 data nodes, let's say we go and give 50 to each of them, right? And additionally, head node also keeps the ranges saying, for this range, the data is available on data node 1. For this range, data is available on data node 2, etc. Right? Once that is done, data node can go and fetch the actual data from Iceberg table directly. It's not like the head node is fetching data from Iceberg tables and giving it off to data node. That's wasteful, right? Additionally, data nodes again have indexes where they know that number 0 is available here, number 1 is available. Think of a mapped structure there. Now we said that we want to store it nicely, efficiently in memory, but we also want to transfer it over the wire really quickly because remember, GPUs are waiting there, right? And then we use something called zero copy, which is the claim to fame for Apache Arrow. Let's see what zero copy is. So if you look at the traditional data stack, you had all these RDBMS tables, something like Postgres, MySQL, Oracle, or something like that. And while the database has data in columnar storage, when you have the advent of columnar databases, the over the wire is still JDBC, ODBC. How many of you understand JDBC, ODBC? Quick show of hands. Pretty much everyone, right? Because it's been there forever. Now, but we're still using it to fetch data that's there in a columnar database or any columnar storage format. Just because you're using JDBC, what you have to do is you have to convert that columnar data to row-based data to make it travel over the wire via JDBC, ODBC connectors. And on the client again, you have to do another convert box, right? Because you want data in the columnar format. These are the 2 convert boxes that Apache Arrow eliminates with something called Arrow Flight. So in flight, it's columnar data on storage in the database. It travels the wire in the columnar format as well. No conversion anywhere. You actually save a lot of time here. Johnu again talked about the challenge that you have data in a central place, which is the cache in this case, and we want it to be accessible from heterogeneous training jobs. I have an illustration for the same here, where on the left, you see that there is a training job based off PyTorch with 3 workers. And on the right, you have another training job with 5 workers. The amazing thing here is dynamic allocation, right? So for instance, if on the left, if you have the worker with rank 2 asking for data, what the head node will do is it will know that, I have 3 workers. The second one out of that is asking for data. So imagine you again had 90 files. Then it will say, you know what? The worker with rank 2 should get from 31 to 60, the middle batch out of the 3 batches, right? Because there are 3 workers to consume those. But when it is the same rank 3 across 5 different workers, it will make a 1/5 unit of it, and it'll only give that much, right? So now coming back to the sort of protocol itself, you see the arrow with number 1 tagged on it. It first asks for the data, saying I am 2 out of the 3 total nodes, so give me data for me. The response from the head node in number 2 here is these are the URLs that you should go to and ask for these offsets. Now, the worker will directly go to those URLs given by the head node and ping them for that specific data that they have been allocated. Now let's put everything together, right? A lot of different technology that we had to touch. So let's put it all together now. What we do here for the binding agent is something called Apache Data Fusion embedded into head node as well as data nodes. I have numbered the flow for you. So number 1 is get data from the Iceberg table, meta information. Then you make, from the head nodes, assignments of slices of data to each data node. Data nodes, again, have data fusion running on them, and data fusion allows them to store the data that they are responsible for in the arrow format. PyTorch workers then directly get the data from the data nodes that will hold the data that they're looking for. And this is over Arrow flight. So we looked at these challenges that Johnu showed on a slide earlier. For efficient storage, again, Apache Parquet. We want GPUs to be busy all the time. We want network bandwidth sort of to be really, really fastly used. So we have Aeroflight to facilitate that. At the same time, you have a custom, and for Apache Iceberg is there for accessing for a lot of people. You have a cache layer which is tuned for you to access from your ML training workers. And every worker should only get the exact amount of data that it needs. If it is getting more data, the IO is being wasted. At the same time, the GPUs are waiting so that all the data could be transferred. For that, we have this indexed storage. We can very quickly go and get only what I as a worker am responsible for. Lastly, we discussed heterogeneous training jobs, where we earlier saw we had 3 workers and 5 workers, and each could get data depending on how many workers are there on that training job. So I'll hand over to Johnu again to quickly show you the API as to how you initialize this cluster and use it.
Yes, so we have talked about various technologies here. So the idea is to make simpler, not making it hard. So from a training perspective, what we have to do is give a simple SDK where you can do all of these things in a single command, right? You don't need kind of like all the technologies in your training code. That is not something that can work with any data scientist. So from the Kubeflow trainer, there's a simple train function where you have to provide a train function that you have to, the train underscore func, that's a function that is getting run across multiple nodes for your distributed training. So here what I'm saying is I have a train underscore func, which will be run in 3 nodes, and each node having 3 CPUs, 6 gig memory, and 1 GPU, right? And I'm going to use an initializer, the Arrow cache dataset initializer that we talked about, where the data will be sharded across 3 cluster nodes. So after that, everything is magic. It actually works. The whole code is there in GitHub. Please take a look at that. Huge shout out to Akshay and Trey Rasek for the initial PR. We have a design doc, issue tracker. We really want contributors to test it out and add more features to that. We have issue tracker there. We have a detailed proposal if you want to dig deep into that, and a PR with the implementation for all things that we have talked about. Questions?
Are there best practice guides also in the suggested solution?
Yes. So if you see the SDK, there is very less chance that you can make mistakes. So the only ones which are needed for your training, that is what it is exposed. So for this is the SDK is primarily for a data scientist perspective, while for your platform admin, you have all the flexibility to change your resources.
Yeah,
and
I
then
was
schedule
wondering
it.
from
Yes.
a platform admin angle.
Yes, yes.
For
So-
example, all my nodes need not have 6 GB GP.
Yeah, you're right. So that is actually there in the YAML itself. So when you apply this, it gets converted to YAML, which is a custom CRD itself.
Which I can go and amend
Yeah,
myself.
exactly.
Point taken.
Yeah. Can you pass over the mic?
You guys are using Arrow for cache optimization, am I right? Let us say if I have some predefined framework like say PyTorch, or let us say if I'm working on a Java-based code rather than Python, can I skip the whole Arrow or Apache Arrow for that if I already have an implementation in say Java? Basically my question is Apache Arrow the only reason because we're working in Python?
Arrow is basically a multi-language toolkit, right? So even if you go back to the architecture, your PyTorch is in Python, but data fusion, the head nodes and cache nodes in general, those are written in Rust. So Arrow has libraries for Python, Java, Rust, you name it, you have it, right? So you can have a Java-based SDK for Arrow similar to PyArrow, and you can use that, right? So the Spark example that you took, written in Java, it can consume Arrow very easily using the Arrow SDK for Java.
I see that you used the reference to a metadata JSON. So are we querying some kind of data catalog to fetch the location of the table format?
Yes. So he would have explained that, right? In the head node, the head node actually has the information of that, and that is what it is actually given back to the application code in order to fetch data. Like say what happens during training, like as I said earlier, is from a distributed sampler, PyTorch gives what is the data that I'm looking for each worker. Now it contacts the data node, where should I basically read for, and the data node gives that information which will be taken forward for your training. Okay. That's the metadata information.
So suppose a scenario where the data is being ingested by a different workflow, and this is pulling the data from a different workflow. The Iceberg, the metadata has some UUID format, right? So that keeps on evolving.
So this is just an initializer part, dataset initializer part. You can skip it if you want, if you are actually using a different way of doing it. So internally what it does is it uses something called a leader worker set, which is again a Kubernetes, which creates this head node and data node, etc. But it is up to you how you do that. Like it is not strictly required, just the implementation part. Yeah.
Parquet file finally decompressed at the PyTorch worker only. Am I correct?
Sorry?
Parquet file finally decompressed at PyTorch worker job only, right?
Yes, yes. So if you had data in the Iceberg, what you would have to do is you have compressed data sitting in Parquet, you have to decompress it, and if you don't have that in between cache nodes, the GPU has to actually access data, which will be compressed data. GPU has to sort of be spent on decompressing that data, right? We don't want to do that. We want GPUs strictly to be used for training. That is why we introduce in between an Arrow format, which is a very natural. You don't have to do any conversions, anything like that. You just get data and use it. So minimal thing for the GPU to do. So, I mean, when you are asking from PyTorch, then you don't have to decompress anything. That's the whole point of this middle cache layer. You have decompressed and kept the data just consumed, ready for you to use.
Basically, that is the Arrow flight that we talked about, right? It actually issues. Yes, yes.
So, what we are doing for the resiliency, like you are sending into a distribution, right? And what one epoch fail or something happens to there.
So that is primarily with the PyTorch, right? Now, like there are multiple ways to do it. Like say, for example, in one PyTorch worker fails, by default, what it happens is that entire thing will get restarted, right? Your training got lost. Whatever progress that you have made, that got lost. There are multiple ways. For example, you checkpoint at regular intervals, and then you take from the last checkpoint, you start reading it so that like every worker gets a last state and continues from there. So yeah, that is a separate discussion altogether.
Have you hit any limits in while using Arrow, or how much of data would you cache? And yeah, basically, what are the challenges that you saw while adopting Arrow?
Like, can you be more specific there?
Not all your data can be cached, right? And there are always limits that how much you can cache, and most of the I've had cases where the cache kind of gets filled up, and then the whole data is not like it's not asynchronous, so it has to either recache it or things like that. So,
Right.
Have you hit any limits,
So-
or have you seen issues such?
Yeah, this is actually the first version of the implementation. So the assumption really is that you are putting all the data you want to use for training into the cache. But yeah, I mean, there are some future work planned on these. So you can go through the design and look at future work. And we really think that it could be really nice to have contributors who can work on some of those. So that would be actually a great task to do, right? Because you don't have so much RAM either, right? RAM is not free of cost. But then compared to sort of GPUs, it's still okay, right? So maybe, yeah, you can use that. Or I don't think you can have a hybrid case where some data comes from the cache nodes and some data comes from the Iceberg nodes, unless you do some trick there yourself for now. But that's a great proposal. You could probably file an issue on GitHub and somebody could work on it. Yeah, thank you.